So you can see the region W, it's a cone. And let's see what we got going on here. We said the angle at the vertex is 2 pi thirds. So that's going all the way across. That would be going from one end to the other. So half of that would be just pi thirds. And then the height is 1 rad 3, 1 over rad 3. And then they want you to set up Cartesian, cylindrical, and spherical. All right. Um, I'll tell you right now that if you were to do this, I mean, really of the three, cylindrical would be the way to go. It'll work with Cartesian, but you'll have radicals. And you pretty much don't want to mess with spherical unless it's actually part of a sphere. This thing is flat on top, so it's not really a sphere anymore. But let's give it a go.
Yeah.
Let's see what we get. So we want to do Cartesian, and then, well, I've got all I need. What I'm going to do now is just I'm going to unshare, and then I'm going to go to my um, overhead. And then let me get that going here. So we need to figure out what the equation of the cone is for starters. And so what I'm going to do is I'm going to draw this picture. I need to figure out just what are these lines, and if I can get part of it going, the rest of it follows pretty much naturally. So I know that the height is 1 over rad 3, and I know that the angle is pi over 3. And so what I would do is, well, I'd like to figure out what this length is, and that would give me the x value. And then I can use that information to figure out the actual height of the cone or the equation of the cone. And so what I'm going to do here is I know that, so what I have here is I have a triangle with opposite, which is unknown, or x. The adjacent is 1 over rad 3, and the angle is pi thirds. So I'll relate them with tangent, and it's opposite, so I'll call it x over 1 over rad 3. And then at any point, stop me if you have any questions. This is kind of the big leap right here. Once I got this, the rest of it just kind of falls into place. Now, tan of pi over 3, does everybody remember what that one is? That's going to be rad 3. I have to kind of go through that myself too. Yeah, it's going to be radical 3. And so I have x equals then 1 over rad 3. And if I multiply both sides by 1 over rad 3, turns out x is 1. So it looks like x is 1 right here. So this is the point 1 and then 1 over rad 3. Okay. Does that make sense? Again, stop me if you at any point just go ahead and pipe in and let me know. And so now I need the equation of the cone. In general, the equation of the cone has this form. Okay. It's the radical of x squared plus y squared and then some coefficient in front. And I find it convenient actually to put the coefficient inside the radical. And so what I know is that, I'm sorry, that should be a z. My bad. And so for example, right here, since the cone is symmetric, right here at x equals 1, that's the same as y equals 0. That'd be like being right here or right here on the xyz axis plane. So at x equals 1 and y equals 0, z is 1 over rad 3. So we can figure out what A is. Looks like A is going to be 1/3. And all right, we'll go with that. So the equation of the cone is going to be this. Okay. The equation of the flat top is Z equals 1 over rad 3. So if I want to set this up using Cartesian coordinates, I'll have a function somewhere in the middle. I'll just leave it blank. I'll have dz, dy, dx. And so I would come up from the bottom. I would hit the cone. Doesn't matter where I hit it. I'm going to hit the cone somewhere. So the bottom bound will be the cone equation. And the top bound will be the plane equation. So far, so good. Natalie, I think you were the one that asked this originally. Is this where you were just helping?
Yep. Yeah, this is helping a lot.
Okay. Now we're done with Z. So what we do now is we come back into the picture. We just kind of look at the shadow that it makes now on the XY plane. And that's just going to be a circle of radius 1. So in the XY plane, it's just a circle of radius 1. And so let me write that out. I'll actually write that out in words. In the XY plane, the region is a circle of radius 1. And so the formula for that would be y equals, well, actually it should be plus and minus 1 minus x squared. So the bottom bound would be negative 1 minus x squared. The top bound would be negative radical 1 minus x squared. And the top will be radical 1 minus x squared, so plus. Then the x bounds will just be negative 1 to 1. Okay. That's the Cartesian setup. Okay.
Okay.
Um, Go ahead. I'm sorry.
So this is all going from the tangent of pi over 3, basically.
Yeah, because we need to know, like, really, I just need to know, I need a point on the edge here. I need to know how far out does the cone extend over the XY plane. And so I just kind of drew like a side view. I know the angle coming off the z-axis is going to be pi over 3. I know the height is going to be 1 over rad 3. I don't know what this guy is. And so I just work it out. I know that the tangent is opposite over adjacent. So tangent pi thirds is opposite x over adjacent, which is 1 over rad 3, and I just work it out. Once I've got that, and it turned out to be 1, so I'm happy with that. Once I've got that, I've got pretty much all I need to generate the equation of the cone, and then, of course, the circular shadow that it creates on the XY plane.
Mm,
Does that help?
yeah.
Okay. Let's run through the other two because actually they go a little quicker. Maybe I can do it on the side here. Let's see if I can shove it over there. Let's see. So for cylindrical, well, what would I do on that one? I would keep the Z, I would keep the DZ, but then change the X and Y for dr and d theta. And the reason for that is that the X and Y create a circle. It makes most sense to um, trade them out for the cylindrical. And the good news there is that we can read off the bounds for the circle immediately. So the first of all, that R has to be there. That's the Jacobian. And then so this circle is radius 1, so the bounds for R would be 0 to 1, and then you're going all the way around, so theta would be 0 to 2 pi. So that creates the bounds for the R and theta for the cylindrical. for the for what's over here, I would actually just keep this. This is going to be x squared plus y squared. That's r squared. So square root of r squared is r. So it's going to be r over rad 3. And then it looks like up here, nothing changes, 1 over rad 3. So that would be cylindrical. And again, did everybody catch that? This is x squared plus y squared is r squared. Square root of r squared is r. And so really what I have is radical 1/3, and then r. And I just put the radical in the width of 3. Okay. Let's go ahead and knock this one out of the park for spherical. All right, let's see if I can cram it in there. Um, it's the Jacobian is going to be rho squared sine phi d rho d theta d phi. The theta bounds are just 0 to 2 pi because that's the circle going all the way around. The phi bound is actually just what you see right here. It's just the lean from the z-axis. So z-axis is 0. So it's going to be 0 to pi over, I'm sorry, pi over 3. In fact, I just realized something here. This is actually correct, but I don't have to rewrite it. I can't, I'm going to have variable bounds on the edge, so I can't do that. So sorry about that. I'm just going to switch the order of integration. Same Jacobian, rho squared sine phi. And I realized that my row bounds are going to be actually I had that right. Oh darn it. All right, my bad. I just realized I had that right. So those phi bounds will be 0 to pi over 3. Theta bounds are 0 to 2 pi. The row bound will be, the bottom bound will be 0 because you're starting at 0. The tricky part is the top part. And this is where you
Oh,
just use the rule that in from spherical to cylindrical, I'm sorry, from spherical to what's the word I'm looking for? Cartesian, you say that z equals 1 over rad 3. Well, the exchange is um gosh, rho cos. I can just look at the picture. Let's see. It's going to be um give me a second here. I'm having a little brain hiccup. It's going to be rho cos. I want to make sure. I think it's going to be the phi. Yeah, it's going to be rho cos phi. I just want to make sure I get the right variables there. So I divide it out by cos phi, and I get this strange looking thing. And if you don't like that, 1 over cosine secant. So you can actually use the secant.
you're a little bit outside of the
Oh,
frame.
I'm sorry. I'm sorry about
Thank
that.
you. Thank you.
Okay, so let me repeat myself. The top bound is z equals 1 over rad 3. The exchange for z is rho cos phi. So I just simply make the exchange. I'm solving for rho, and I divide out by cos phi. And I could leave it like that. That looks a little funny. So 1 over cos is secant. That looks a little cleaner. So it's going to be 1 over rad 3 secant phi. And that would be your spherical integration. And that you'll never actually do this. There's no reason to ever turn a region that is not spherical into spherical coordinates because the whole point of spherical is to avoid non-constant bounds. You can do it, you can force anything, but this is going to be a rough little problem here because then you're going to have to integrate secant. So anyway, so
So
there you
probably the way
go.
to go would be cylindrical, right? Mhm.
Yeah, if you actually had to perform an integration of the three, this is probably the one you want because it's clean. It's got nice, easy bounds. You can just kind of look at the three and just look that this one looks friendliest.
Is there a way to visually kind of like see which one is the easiest one to solve and then just convert from that?
You mean like which of the three, like Cartesian, spherical, and
Yeah,
circle?
because from seeing it, you basically knew that cylindrical was the easiest way to go.
If if the region is a sphere or part of a sphere, use spherical. If the region has a circular aspect to it, use cylindrical. Otherwise, use Cartesian.
Okay.
This region here, this body, is a cone with a flat top. It is not spherical. That's the key. If it was spherical, it would have a nice little, dome on the top, right? Um,
Yes.
so it's not spherical. So right off the bat, I would say I'm not going to use spherical to set up the integral. I could, I actually did, but I wouldn't do it because I would immediately revert to cylindrical because I can see the circular aspect. There's some circular aspect to the shape that immediately gets me thinking about cylindrical. And then
Okay.
if it's just any other shape like parabolas and cubes and rectangles and slanty slopes and stuff like that, I would just use Cartesian.
Okay. Good to know.
Yeah, I'm glad that worked out. I know that there's been some issues on this question. There's been a typo issue because I know that on some of the questions that people have had, their problem has like a slash. It's like one over rad three, but actually, if you take the slash out, then it works. So I've been working with our people here because I don't have direct access to the Infinity people, but we have some people in the department that do. So I've been kind of going through them, trying to clear that up. So all I can say is be patient on that one. There's been a couple threads on ed discussions about that, and in one case, we got it to work out by just removing the slash, and it took me about a half hour to figure that out. Drove me nuts. All right. Any questions on this one?
All good on my part.
Okay. Anybody else have any questions on this one? Well, you can see them right here. What's the radius of this sphere, or the first one?
7 and
And
8.
right. So that's going to set up some bounds here. So I've got it copied down. And so I'm going to stop the share and go to my overhead. All right, let's see what's going on here. First of all, let's get the bounds figured out. We're doing this in spherical. So we've got three variables, uh, rho, theta, and phi. This symbol, by the way, is a Greek letter rho. Um,
Apologies.
and the bounds for rho will be 7 to 8. Since it's a full sphere, theta is 0 to 2 pi, and phi is 0 to pi, because phi is like the North Pole to the South Pole. 0 is the North Pole, pi is the South Pole, the equator that would be on the XY plane would be pi halves. So it's nice that you have constant bounds. And then, so let's see what we got going on here with the here. So it looks like a mess, but it's actually not that bad. First order of business, I'll tell you what, I'll come over here. Let's take out the x squared plus y squared plus z squared. That is rho squared. And on the bottom, we have radical rho squared, because the definition of rho, it's basically the Pythagorean um, formula for x, y, and z. Now, this, of course, is just rho because radical and the square take care of each other. And then, so that comes down here. You got e to the negative rho squared all over rho. And then you've got your Jacobian rho squared sine phi. And then you've got your d rho d theta d phi. And if I put my bounds on, rho is 7 to 8, theta is 0 to 2 pi, and phi is 0 to pi. Now I can clean this up even some more. Two of these rows, well, you have two up here and one down here, so that leaves one on top. So I have rho e to the negative rho squared, and then I have sine phi. And that's my integrand. And I'll pause there for a moment and just make sure you're okay with that. Does that make sense what I've done there? Okay. All right. Uh, as far as integration goes, let's do the row integration. This is just going to be U to U substitution. So I kind of ignore everything except for the rows. So ignore these and that and ignore that. So we're just looking at the E stuff. So all righty, so that's just good old Calc 1 stuff. So when I integrate that, I get let's see, it's going to be have to do use that, so 1/2. So it should be 1/2, should be -1/2 e to the negative rho squared. And I'm going to double check that by taking the derivative. The derivative of e to the negative rho squared is e to the negative rho squared times its derivative, which is -2 rho. And the two, yeah, we're good. So then I put in the 8 and the 7,
Yeah.
and I get negative e to the
Ask a quick
negative
question.
64. Take away e to the negative 49. These are tiny numbers. Wow.
So when I was
Yeah.
looking at this, I was basically considering rho kind of like an x. And if we had x times e to the negative x squared, that when we're integrating, we can't have two variables. Could we have no, we couldn't have them multiply each other. We'd have to do something to not have them multiplying each other. But we didn't care about that here.
I'm actually okay. In regards to this guy here, the sine phi, I'm just ignoring it entirely. I'm concentrating solely on the row stuff. This is all I'm integrating because this is really just being a spectator. It's held by multiplication, and so it's just going to sit out in front. So I just don't want to keep on writing it. So this integration is actually a chain rule, and it's a U to U substitution rule. So if I let U equal negative rho squared, then du is negative 2 rho.
Right.
I have to put a -1/2 to balance it.
Right. But then if we do that substitution and we have the -1/2 e to the negative rho squared, then I'd take the integral. And then
We're
I'd do,
done.
I
No,
think,
that is the integral. That is the antiderivative.
oh, is that what I'm doing? I guess I need to revisit substitution. I thought there was another step.
I kind of combined a couple here, but that is the antiderivative. The way I check it is just take the derivative of what you see right there. It'll be e to the negative rho squared. Okay, it copies, but then the derivative of negative rho squared is -2 rho. Well, the negatives cancel and the twos cancel and just leaves the rho, and you're back to right here. So that is the actual antiderivative.
Mhm.
Now, when I pop the numbers in, I get this crazy thing. And if I put that on my calculator, I'm just going to get 0. These are tiny, tiny, tiny numbers. I'll tell you what, I'm just going to put a little blob around it. We'll just come back to this guy. Let's go ahead and work out the other integrations. The theta integration, there is no theta here. So when I integrate d theta, I get theta, and then I just pop on the 2 pi and the 0, so I just get a 2 pi. So the integral from 0 to 2 pi d theta is 2 pi. So that'll get absorbed in. I'll do that at the end. And then the last thing I need to do is I need to take care of this sine phi, and that's going to be from 0 to pi. So 0 to pi sine phi d phi, and that's going to be negative cos phi from pi to 0. Just got to be watch out. So watch out your negatives here. Negative, and then cos phi is actually -1 minus negative, and then when I put a 0 in, so this negative here is this negative here, and I put a 0 in, I get 1. So it looks like I get 2. All this is just 2. And then so the final answer is just the product of these three things. And so these I'll just cancel out the two. This two and this two will just go away. So I'll have negative. Let's see. This two will survive. Negative 2 pi, and then this weird number. So the product of all three. Okay. Does that help you?
I think, like, I'm still confused, but I don't want to waste everyone else's time, so I guess I'll
Well,
just,
I
um,
think, is it this step right here? Because I think we can resolve it here pretty quickly.
it's two things. It's why when we have an exponent squared, that's not the same as 2 times that exponent, because like when you're raising an exponent to another power, you're multiplying those together. You're not actually exponentially raising an exponent.
Actually, you
So
are. You are in this case.
in this case, but not in
Yes.
most other cases.
Well, you may be confusing this rule, like we have e to the row and then like that.
Mm, no, I mean, like if we had x to the 5th raised to the 2nd power, it wouldn't be x to the 25th, it'd be x to the 10th.
Right, that's correct. But that's not what
But
this is. This actually is
like
this is actually a stacked square or stacked what they call I forget the name now, but it's basically a tier of exponentiation, a tower. Actually, that is a name for it.
you could, so whenever I see an exponent squared in a tower, I can't consider that multiplying it by itself.
No.
Okay, well, I mean, that's good to know. Don't know how I
Yeah.
missed that all this time. Um,
Yeah, that's this guy, this two is stuck where it is.
okay, good to know. And
Sure.
then when we do this U du substitution, because I did the same substitution, and then I thought that's still in the integral, because then I'd have all that times du because I changed dp into du. That's what I thought I did. But then you're saying that's like it, that's like the end
Well, I'll
without.
go ahead and show you the steps. So you would set u to the power negative rho squared.
Yep,
The derivative is negative 2 rho d rho.
yep.
And what you're going to do is you're going to take the integrand, which currently is rho e to the negative rho squared d rho, and you're going to make some substitutions. This becomes e to the negative u. Actually, it just becomes e to the u because the negative is part of the thing. And then these two guys, the rho here and the d rho here are these two right here. And so they get, I have to put a du here over negative 2 because I have to solve for rho d rho. And
Right.
that's this negative 2 falls down here. So they get negative 1/2 e to the u du. And that's where this negative
I was
1/2 comes
considering the
from.
u negative
Well,
after.
I put the negative in with it.
That's what I did too. I was doubling it up. Thank you.
Sure. But
Okay.
this negative still lives on. That's the problem here. It still is there.
Yeah, it's considered.
Now, one thing I would recommend to all of you, and I still do it after all these years, is a lot of times I'll do a U to U in my head, but I'll also do a quick check by taking its derivative just to make sure I get this guy again. Okay, so just take a quick derivative to make sure you got the original integrand. All
Fill in
right.
holes in my reasoning. Thank you.
Yeah, no problem. Happy to help. Any other questions on this one? All right. So we're looking at number 8 here, 12.5. Let me copy the information here. We've just got a generic triple integral f and then dv. E is the solid bounded by z equals 0. That's the XY plane. X equals 0. That's the YZ plane. The plane Z equals Y minus 8X. And the plane actually Y equals 16. Now, the first order of business is just to figure out what this thing looks like. If you can see this object, it makes the problem so much easier. And unfortunately, even with all the grapher tools out there, it's not the easiest thing to do. So a lot of times you're just going to have to kind of think it out. So Z equals 0 is the XY plane, and X equals 0 is the YZ plane. So if I draw my usual XYZ axis system, one of my bounds is actually this plane down here, the floor. And then another of the bounds is the YZ plane. It's actually this plane, this wall over here. So those are two bounds right off the bat. And then Y equals 16 is going to be way out here. Now it's not just a dot, it's actually it itself is a plane. It's the plane that is, well, again, I'll just kind of, it would be a plane that kind of crosses through parallel to the XZ plane. The XZ plane being Y equals 0. So Y equals 16 is 16 units out. Now this guy here comes into play, and so we need to figure out what does this thing look like? Z equals Y minus 8X. So, um, well, I don't know. Let's figure this out. So I'm thinking of a couple ways you can do this. I would probably, I know it's going to pass through the origin. I just need to, let me think this out. It's going to have, when X is 0, okay, when X is 0, I just have Z equals Y, and that's going to be the 45-degree line. So it's going to be like the shadow on the wall there. And when Y is 0, I've got Z equals negative 8X, and I've got to, let me make sure I copied that right. Yeah, I did. All right, give me a second here. I have to think this one. I need to see it. Once I see it, I get it. I just have to see it. So Z equals Y is going to be that line up there. Z equals negative 8X is going to be a line. Well, it's, in the way I'm looking at it, it's actually going to be below down here. I don't like that. So Z equals negative 8X. You'd be looking like that down here. So what the heck does that look like up there? Give me a moment here. I need to really kind of wrap my head around this. I'm just trying to see it. The problem here is that it seems to be an infinite sized region. I'm not, You know what? I hate to do this, but I'm actually, I think you should do this sometimes. I'm gonna cheat. I'm gonna actually look this up on Desmos, and I'm gonna do the 3D grapher because I'm not seeing this. I need to actually see it. And I encourage you guys, you'll have the 3D access. I'll bring this up on my screen. I just don't see it. Okay, give me a second here. I've got it. Um, so Z is, so let's orient this in the usual way. I would have, okay, I'm starting to get more of a feel for this now. All right. This is the way we would orient it. And okay, I feel a lot better. I just wasn't seeing it. Let me copy this as best as I can. Can you guys see my cursor when I move it?
Yes.
You can, okay. You can kind of see, okay, this grid down here is Z equals 0. That's the floor. You can see this shape, the red plane goes up, and it's going to eventually intersect the YZ plane, which is X equals 0. It's going to create a very narrow kind of triangular shape here. I'm going to try to draw that. Um, all right. I think I'm much happier now. And you'll have access to these Desmos features on the test, so you can certainly put them on there. Um, okay, now that you saw that, look at my terrible drawing. What do you think of it? All right. Um, but it is a four-sided object. It's composed of triangles. It's pretty narrow. The bottom is the z equals 0, the xy plane. The back side is x equals 0, which is the yz plane. The front face here is y equals 16. And then this slopey guy right here is z equals y minus 8x. All right, well, boy, that's the big hill to climb right there because the rest of the problem then is just a matter of setting it up. So let's do a couple of forms here. So let's do dz dy dx. Okay. And so if I do dz, I come up from the bottom, I hit the bottom, which is z equals 0, and I exit out the top, which is y minus 8x. Okay, so those are the z bounds. And then immediately what I do is I look at these two regions and I look at just the bottom itself. And I'm going to redraw that. It's going to be it's going to be in the xy plane. It's going to be 16 up there. It's going to, let's see, right here, that would be the point. If that's 16, that would be 2, so 216. Okay, so this equation right here is y equals 8x. And this equation here, of course, is y equals, or I'm sorry, x equals 0. This is y equals 16. So if I do dy next, and I come up this way, I'm sorry, I come up this way, I enter the region here, so my entry bound is 8x, and my exit bound is 16, and then my x bounds are just constants 0 to 2. Okay, so we've knocked out one of them. Does that make sense?
Yeah, for the middle, the dy, the middle one, you just took that y minus 8x, um, and you, I don't know what happened.
Well, I basically redrew the bottom right there. I drew the footprint. So this is the bottom of the object, and it's only in X and Y. So I redrew it down here in the usual orientation where y is this way and x is this way. And I just had to kind of figure out, well, this is y equals 16 right here, this little line. And then on this line that connects up, well, it has to connect. I had to figure out, well, if y is 16, if I put a 16 here, then that would have to make that a 2, okay, to make it all work out. Another way to look at it is that when you're on the XY plane, z equals 0, right? And so if you just pop a 0 in there and just move the 8x to the right side, you have y equals 8x. Okay. Um, let's do another one. Let's do the same triple integral, but let's do dz, dx, dy. Since I've got the thing all drawn, dz doesn't change. This time for dx, I would draw my arrow this way, and I would be entering at 0, and I'd be exiting, and I have to solve for x, so it would be y over 8. My y bounds would be 0 to 16. Your outside bounds are always constant. Does that make sense? I'll do one more if you guys are cool with that. Let's do, how about dx dy dz? Let's just flip it around. Okay. So now I'm going to come back to this object here. My first arrow is being drawn in the x direction. So it's actually going to enter through the back and exit out this sloping side here. So it enters through the back, which is 0. And it exits out this sloping side here. Well, I need to solve for x. So z equals y minus 8x. I'll do it over here. Z equals y minus 8x. Oops. So that means y minus z equals 8x. And that means x is going to be y minus z over 8. So 1/8 y minus z. Okay, so that would be the bounds for the x. And then what I do is I look at the yz. So I'm done with x now. I just look at the triangle in y and z. And so I'll draw that in the usual orientation where y is this way. Sorry. Y is, which you see right here, z is here. And let's see, I know this is 16, so it's going to be 16 up here. So something, 16, something. X would be 0, so that means z would also be 16. Okay, so I've got a line here in the YZ plane that's just basically 45-degree line. It's looking like this. This is the region. So this is going to be z equals y, and this is going to be the point 16, 16. So if I do dy next, I draw the arrow this way, and I enter, well, I have to solve for y, so y is z, and then I exit out at y equals 16. And then the z bounds would also be 0 to 16. So far, so good.
Yeah, this is helpful. Thank you.
Okay, and then the other 3 are kind of like it. You just swap them around. Any other questions on this one? All right, we got a few more minutes. Any other last questions? Let's see. Any questions from 13.1, which is the section on uh, vector fields? What are you doing in that section? Okay, you're doing some gradients. Um, mine didn't come through for some reason. Interesting. Um, I would recommend on this one to, not hand draw them, but to maybe Desmos has a vector field plotter, and or maybe just Google vector field plotter. There's a lot of good ones out there that where you can pop in the component functions and see what the vector fields look like. when I teach that in class, that's what I always do. It takes forever just to plot a lousy vector field. So it's more important that you just kind of get a sense of what they look like and know that you can plot them quickly using a plotter. Um, when I went to my 13.1, all the regions, all my shapes didn't come through. I got these, oh, there they are. Oh, that's weird. I got those, that blank, that broken link symbol. Any last questions?
Thank you so much for all the help and for the homework extension.
Yeah, sure. I realized because I'm not available on Thursdays, so I figured a couple extra days would help, and that way I could at least have this Zoom with you guys. Um, well, we've got a little over a week. What is it, like 10 days, 9 days? So hang in there. The irony is that I think that this last module with line integrals and surface integrals and flux integrals is really fascinating stuff. And if you're going to major in electrical, especially if you're going in electrical or fluid, um, thank you. If you major in electrical or fluid type dynamics, whatever, you'll see a lot of this. So I know it's been a lot of hard work, but this last module is probably the most interesting of them. And I have lots of notes on my website. So, no, you're welcome. Yeah, I have lots of notes on my website uh, and examples. So if I'm not available, go to my website, dig through my notes. You'll probably see an example there that'll probably help you. Alrighty.
I
Well,
like the two
gang,
kittens you put in one of your presentations there.
what's that?
The little cats you put in one of your presentations there.
Oh yeah, yeah. Oh yeah, I threw one in there just to kind of surprise you. Yeah, one of my kitties always wouldn't leave me alone when I was typing, but that's probably common, right? Um, yeah, I am going to post this video. It'll probably be about another hour or two. So, all right, I'm going to go ahead and stop, and you guys all have a pleasant couple days, and see you again in a week or so. All right, bye bye.